Welcome to this quantum security and defense presentation toward quantum enhanced data centers. And thank you for being a valued member of our community. Marc Kaplan has worked in the area of quantum information for more than 15 years. He received his PhD from University Paris-Sud and worked in Montreal with Gilles Brassard, the co-inventor of quantum cryptography, before founding VeriQloud. His research is focused on using quantum algorithms to break classical cryptographic systems and on the design of quantum-resistant alternatives. He is the CEO of VeriQloud, a company developing solutions for long-term security based on quantum technologies.
Thanks a lot. Thanks a lot, Anna. Thanks a lot to everyone for being here today. So let me share my slide. I guess you can see my deck now.
Yes.
And you can hear me well, right?
Actually.
Okay, so let's go. Right, so today I want to present you a bit of our findings at VeriQloud from years of developing systems around quantum cryptography and quantum communication. So it's so I mean I will in the course of the presentation I will tell you what we're doing, but the main message that I want to convey today is this vision that we had since the beginning is that if you want to expand the range of opportunities for quantum communication technologies, you need to work out on applications. The more applications there would be, and the more stakeholders will get involved. So it's not so much about detailing very a lot our different products. It's more to tell you about this vision, to share this vision with you, and show you both the short term and the long term of this vision. So working on quantum network applications is something that we've been doing for a while. Here you can see some of the deliverables of various projects that we've participated in. We've been contributing to this quantum protocol zoo that we're still hosting at the moment. It will probably move not so long from now. It's just a wiki of quantum communication protocols for quantum network applications. With my dear colleague Mina Dusti, we wrote this report for the European Commission on use cases. So this is about really translating the scientific literature into something that, let's say, looks practical. And some of my colleagues here participated also to some research based on, using simulation tools to perform benchmarking. Right. So this is just to tell you that we have like a large experience on quantum network applications, and the main the founding philosophy here when you look at quantum networks is that, of course, this is, by the way, at the very core of one of the main projects that we participate in, which is the Quantum Internet Alliance, this EU-based project. And the core observation is that, okay, today we know when we talk about quantum networks, when we build quantum networks, we're talking about quantum key distribution networks. I guess everybody knows here that quantum networks today, they only perform one task, which is quantum key distribution. However, as soon as these networks only require to produce quantum states, send them over, let's say, optical fiber or free space, and then when the party that receives the quantum state immediately measures it, we know that it's producing a quantum state. And the observation here is that as soon as you have more quantum information processing hardware available, as soon as some new hardware for quantum information processing is available, you should integrate it at the nodes of your network. The reason is that it unlocks new applications. So we distinguish usually five different stages. Today we have QKD networks. The next stage is to have quantum repeaters that can distribute single qubit quantum states from arbitrarily from one node to another. The networks that can distribute entanglement, quantum memory networks, and at the very end, of course, quantum computing networks in which you connect quantum computers right? So you would allow any quantum computers to share an arbitrary quantum state altogether. And what I want to do today is walk you through, a little bit of these applications, showing you uh, what exists at those different stages. I of course don't have time to make a full review of everything, but show you also what we at VeriQloud focus on mostly. And the first stage is the stage of QKD networks. I'm not going to describe QKD here. I assume that most of the people know about it. Again, with QKD, you only do one thing, is establishing shared encryption keys between pairs of nodes in the network, and actually between adjacent pairs of nodes in the network. You need a direct connection to establish this shared secret key. And one of the applications that we believe is of interest for many people is that once you have a QKD network, you can also use it for distributed storage. Right? This is based on a protocol that was introduced by researchers from Germany and Japan a while ago, showing that you can, on top of your QKD network, you can use a classical encryption, which is called a secret sharing scheme. And using this secret sharing scheme, you can distribute the data over the different servers connected to your network, so that an eavesdropper that wants to learn the secret data needs to attack several servers. And with the quantum layer, you can have a constant re-encryption of the data, that sort of like constant redistribution that forces even the eavesdropper to attack all of the servers at the same time. So it's a very strong security model. In practice, what we say is that the security. So basically, here you only use the QKD layer to distribute or to secure the distribution of the secret shares. So what you get is that you transfer the security from the communication layer to the storage. Right, you get all the benefits of quantum cybersecurity transferred to the storage. So we're talking about everlasting security, quantum resistance, etc. So this is again software that is known. We have an implementation, like a pure software implementation of this protocol, Linkos. So we call it CASMAT. It's just a distributed storage over a QKD network. It's easily interfaced with any QKD system, and it's up and working. And if you want to test it, just drop me an email. It will be very easy for you to try it on. We have some news here. We did some research that we made public this research last week, showing that you can also improve the situation by using not one QKD network, but several ones. It seems obvious, but it's not. It's not that clear, because between the different QKD networks, you would use post-quantum cryptography, classical links secured by post-quantum cryptography. But nevertheless, by modifying the original protocol, we get that these classical links, although they are less secure than the QKD networks, they are not bottlenecks. So just by modifying the classical part of the encryption, what we get is that an eavesdropper now needs to attack either, get the data from several of the QKD networks, or one of the QKD network, and break all the post-quantum cryptography secure links. So I personally like it very much, because it looks very much like the current deployment of QKD networks, where you have several. Especially in Europe right now, we have lots of deployment of QKD networks at the metropolitan area scale within the various EuroQCI projects. Okay, so once again, this is something that we are deploying on a test infrastructure at the moment, and hopefully in the next coming years we'll have these small quantum enhanced data centers for storing the data all over the world, connected together with PQC connections. I want to show you what happens before. So again, here, right, everything happens at the QKD network stage. So this is already available. This is what is being deployed. But what happens next? Repeater networks, again, so the piece of hardware that you add is a repeater. And the reason you want to do that is that you unlock a new application, which is confidential computing. It's not a new application in the sense that you already have it available with classical over the classical internet. There are various solutions for that, but the quantum networks have a provable advantage here. So what is confidential computing? You want to be able to compute a function whose inputs are distributed over different parties, but you don't want to reveal your inputs. Right. So for example, here on my example, it's just the intersection of these two databases. And of course, it has lots of applications. We're talking about fraud detection in banking, with private medicine, federated machine learning. All these applications are super important. In all these applications, privacy is very important. And we know now that quantum communication networks have a provable advantage for those applications. Next stage are what I like to call memory networks. So now, if you have quantum memories, right, that can store the quantum states at each node, you unlock a whole range of applications, which we still investigate. I mean, we investigate their usability, and it's everything that revolves around unclonable cryptography. So these are quantum tokens that they come with a physical guarantee that they cannot be cloned, encryptors that also cannot be copied to another server, or data storage that if you ask for the server to erase those data, the server can give you proof that it's been erased. And from there, I'm going to jump at the very end of the story, which is the quantum computing stage. So here now, I imagine you're in a world where we have quantum computers. There's a very good reason to connect them to quantum networks. And this reason, again, is privacy. So you have quantum computers today. I mean, they don't do anything that you cannot do on your laptop, but they exist, and most of them are connected to cloud, right? You can connect, like on the left here on my slide. This is the old interface from IBM. It's been up and running since 2016, I guess. But when you use it over the internet, you have to send a clear copy of your program to the quantum computer. What we know, what the researchers have proven, and it turns out, I mean, one of the main actors in the field is my co-founder, Elam Kashefi here. What we know is that once you have, if you can connect your quantum computer and you give to the client something that is very close to a QKD device, you can achieve a very strong notion of security for your quantum cloud computing. First, it's blind. The server doesn't learn anything about inputs, outputs, or the computation itself. And it's also verifiable. If the server tries to deviate from the original computation, then it will get detected. So it's a way to ensure privacy of the data, but also there's a deep philosophical problem here, or at least let's say a deep logical problem here is how can you verify a computation that is happening on a quantum computer without quantum computational power? And it turns out that if you can just send quantum states to the quantum computer, it's possible to do this verification. Here, our effort is very much at the research and development stage. We have recently published some results with in a collaboration with the University of Rome, which has two very interesting features. The first one is that it's a multi-party protocol. So it's not only one client that delegates its computation to the server, but several ones that all together delegate their computation. And the best example here to say how useful it is think about distributed machine learning. You can have one party that holds the data, one with the algorithm, and one with the quantum computer. And at the end, the party with the algorithm would get a trained quantum machine learning model. But without learning the data, and the QPU operator would not learn neither the data nor the algorithm itself. Right, so here the solution is known. I mean, there is a theoretical solution to this problem that has been around for 15 years approximately. But the experiment that we performed last year with the University of Rome is the state of the art today. First, because it's multipartite, and also because it has, I mean, the computation that it performs has some feature that wasn't there in previous experiments. I won't go into details here, but I'm happy to answer questions offline. Before finishing, I want to mention another effort. This whole field of quantum network application, of course, developing a new application is very difficult in the sense that we need to go and ask the people of expertise whenever anything is useful. But I'm very happy to contribute to projects within the blockchain community. There's a new interest, people from the blockchain community that try to identify what are the short-term applications that would be useful for blockchain applications from quantum network technologies. You can go to this website here presenting the whole field. I mean, it's more oriented toward blockchain people to explain them that quantum technologies are useful for something. In terms of cryptography, but it's very interesting to see that there is this raising interest from people outside the quantum world as well to find applications or to find solutions to their problems using quantum technologies. One very good example of very impractical but very good example is one-shot signatures, for example. It has been identified as it's a potential game changer for blockchain, but it's also something that is very long term. So the whole goal is to find things that are shorter term. Okay, so just to wrap up, what I want, I mean, the main message that I try to pass you today is that quantum networks have many applications beyond QKD. Of course, you should start with QKD networks, but after that, add the different hardware available. One thing that I haven't even mentioned here is that all the applications that I showed, they only use pretty much the same states as QKD networks, so BB84 states. This is true for the application to confidential computing, to unclonable cryptography, but also to blind or secure quantum cloud computing. So these states actually can do many things. They capture something that is very deep about quantum information. Designing use cases is a hard problem. This is, I'm talking from my experience. And of course, if I have to name now one killer app for quantum networks, it would be secure quantum cloud computing. But of course, it's also the furthest one because you need quantum computers in the first place. Thank you very much. Don't hesitate to contact me if you have any questions, or I don't know what's the process now. Are we taking questions now or after the next talk?
No, we do the questions now.
Okay.
So we also can have a join sessions, of course, after, but we're gonna take questions specifically for your presentation now. There is a question in a chat from Fred Delogs. What will be if you use blockchain into the quantum process? So I guess maybe more details on the blockchain applications.
Right. To be honest, I don't know. I don't know. I'm not sure. I'm not sure I know of any relevant result here. I mean, maybe there are. I'm not saying there are no relevant result, but I don't know of if there is any. I haven't heard about it. Would be interesting to see.
Okay, anybody would like to ask the question right now? Marc, I have more questions about that because you're using the single photons then for all those applications, right?
Yes.
Could you
Yes. So in all these applications here, as I was saying, you're using something that is very close to QKD as the client. The only caveat here is that in QKD you usually use coherent states. So, using attenuated photon sources. Sorry if it's a bit technical, but the states that you use in QKD are usually not real qubits. They're something that are close enough to qubits that we were able, or researchers were able to have security proof. Showing that it's still secure. It's not the case. I mean, we don't know if the security proof also applies to other applications, basically. But now, if you're happy if you're happy to have clients that can do like real single photon states, then we're only using BD84 states.
Okay, now Michael has more questions. Do you see that also in the chat? So Michael Walker has a question. How can you be sure that the return state is correct and honest? Can't they just return something that looks possible?
I'm not sure what is who's they in this question. Are we talking about the hardware? I mean, usually these applications are all in a model where the security is when the parties they have their own hardware and they have a good characterization of their hardware. It's possible to have something that is lower. So the eavesdropper. Do you mean what happens if the eavesdropper like changes the state and replaces with something else?
Yes.
Yeah. Okay. So for example, where is it here? In this type of protocols, this can be verified.
Yeah. Was how? Oh, I mean, because they're doing the computation for you, and you can't know the answer,
Yeah.
or you wouldn't know how to do it.
Yeah. So what you do is basically you compile your computation by putting little pieces of computation that you can do by yourself. But because everything is blind, no one knows where these computations are. So yeah, you can overcome this kind of malicious behavior.
Okay, thank you.
Questions. Are you exploring QC and federated learning?
Yeah, the answer is yes, but I can't say anything about it at the moment.
And then are you hardening the endpoints with MFA?
Yeah, of course. I mean, here I presented. I just presented like the results at the theoretical at a theoretical level, but when it comes to implementations, yes, of course.
Okay. And then one more question is that is your test only light conducted, or is there also wave conducted in wires between computers and the quantum?
Well, I assume that the question is about if there's only a quantum channel between the parties, or if there are also no. It comes in addition to a classical internet. You usually have a lot of classical information. So it's the case for QKD, right? QKD, you have a quantum channel, but you also need a classical channel, sorry, to perform all the processing.
Right. Any last questions? If not, then I would like to thank Marc. This was great. Thank you for coming and showing us.
Thank you watching these presentation highlights, and thank you for being a valued member of our community. We hope you enjoyed this presentation.